minus K2, then K2. This is larger than 0, and we know that giving K1 larger than 0, for example, or equal than 0, this is larger equal than 0, and K2 equal larger than 0, right? Okay. Well, if you look at this carefully, we know this is K1 plus K2 larger than 0, or equal than 0, K2 larger or equal to 0, but minus K2 is negative. K2 is negative. Now how can I define this larger or equal to 0? What does that mean? A scalar 1, I know 1 larger than 0, 2 larger than 0, minus 1 is smaller than 0, but for matrix larger than 0. You gotta be careful. And this is the key when you look at the matrices. And one more sense. M is a symmetric matrix. Zeta is a symmetric matrix. K is a symmetric matrix. All right? So, for K, a matrix larger than or equal to 0 doesn't mean every term larger or equal to 0 means either larger or equal to 0. No. So mathematicians, they give you definitions. And what is the definition of the positive definite? So this is called positive definite. Well, by the way, the notes is already in the website. So I just uploaded sometime this afternoon. All right, for this matrix, giving any vector z1, z1 and z2, if this is any arbitrary z1 and z2 a vector and pre-multiply the mass matrix and also post-multiply by the z1, z2 transpose. If this multiple them together larger than 0, that for any z1 and z2 except z1 equal to z2 equal to 0. If this condition is satisfied, larger than 0, and for any z1 and z2 except z1 equal to z2 equal to 0, then if this is true, and it happened that this is true, so M1, 0, 0, M2, this 2 by 2 matrix, we call that is positive definite. This is definitions. Mathematicians, they are very smart. They want to generalize the number, the value, from positive number, positive value, become positive matrix, positive something like that. So this one we call positive matrix. For any dynamic system, the mass matrix is always positive definite, doesn't matter what. For any dynamic system, the mass matrix is always positive definite. Careful, huh? Oh, I'm giving you some written problem, you know? You can write it down. All right? If I tell you, say, the mass matrix for a system is positive definite, you have to say yes. Right? Remember that, huh? So you need to write down. Now, again, now another one, positive definite stiffness matrix. Okay. This is the stiffness matrix. The same thing for any arbitrary z1, z2, z1, z2. Then you multiply them out in terms of matrix multiplications. They become k1 z1 square plus k2 z1 minus z2 square. And this will be larger than 0 if k1 larger than 0, k2 larger than 0, any z1, z2, non-zero z1, z2, except z1 equal to z2 equal to 0, then this larger than 0. True, right? Not true? Yes, has to be. it cannot be. If k1 larger than 0, z1 square larger than 0, if k2 larger than 0, z1 minus z2, if they're equal, it's fine. Is equal to 0, but this is still larger than 0. So this is larger than 0. Okay, so the stiffness matrix, this matrix is a positive definite matrix. If k1 larger than 0 and k2 larger than 0. Well, this is very important. I will tell you why. Okay, if this is the case, then this system is a stable system. It won't become unstable. If you have a positive definite matrix, a mass matrix, and positive definite stiffness matrix, then this is, I call, marginally stable. We'll define what marginally stable means. Okay? For positive damping matrix here. Now, if you look at this carefully, now Z1 minus Z2 minus Z2 Z1 and Z2 Z1 minus Z2 square, this can be only larger or equal to 0 because even Z2 larger than 0, when Z1 equal to Z2, then this will be equal to 0. So this cannot be just larger than 0. There's equal sign here. When Z1 equal to Z2, when displacement of W1 equal to displacement of W2, then W1 minus the W2 equal to 0. So if this mass 2 move the same distance as M2, then there's nothing going on there's no damping for the 0, 2. Well, has to be dot, I'm sorry. This has to be if W1 dot and W2 dot, just like Z1 and Z2, if W1 dot and W2 dot, they are moving the same speed, that means there's no damping here. This zeta 2 doesn't give you anything. At that moment, then that's not what we put it there. So, for this case, we call semi-positive definite damping matrix. This is not completely positive definite damping matrix. So, this is except Z1 equal to Z2. All right. Now, that's the definitions. That's just the definitions. There's another positive definite matrix. Let me show you some other positive definite matrix. But there's some property of that. All right. Now, here's a property for positive definite matrix. Okay. Now, what is the property of this? Of a positive definite matrix, based on our definitions. All right. And this, if you are interested, you can look at my notes for that fundamental linear algebra. That note has that. All right. Now, for any matrix, for any symmetric matrix, for any symmetric matrix, you know the eigenvalue of symmetric matrix. For any symmetric matrix, eigenvalue of a symmetric matrix always real. Right? Eigenvalue of any symmetric matrix is always real. They are not complex. They won't be complex. Now, say this is symmetric matrix we call M, right? Just M, so vector M. Then eigenvalue of a M are real. All right? And if the eigenvalue, all eigenvalue are larger than 0. If all eigenvalues are larger than 0, then M is positive definite. So, to check if a separation matrix is positive or not, easier check is just solve the eigenvalue of that mass matrix, that